Okay, we're going to talk about using chords today. First, a quick review. A chord is any segment that connects 2 points on the edge of a circle there. So let's title that A and B. So chord, or line AB, is a chord. Okay, so we reviewed that, or we've done that in the past. So the congruent corresponding chords theorem, as our text says it, in the same circle or in congruent circles. Remember, if they're congruent circles, their radius is the same measure. 2 minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so if we had 2 chords, excuse me there. We had 2 chords, say, we'll call that one A, B again, and go on that one. Call this one C and D. Okay, so we have 2 chords connecting those points on the circle. As long as those chords are congruent, so if AB is congruent to CD, then arc AB will be congruent to arc CD. Okay, so that arc would be congruent to that arc. All right. The perpendicular chord bisector theorem states that if the diameter of a chord is perpendicular to a chord, then its diameter bisects the chord in its arc. So we have a diameter there. We'll call it EC. Switch up some letters here. And if that diameter bisects a chord, intersects it at a right angle, okay, it's perpendicular to it, then the diameter also bisects the chord. Okay, so as long as the diameter is perpendicular to a chord, it will also bisect it. And so if we continue this, let's call that point A, we'll call this one point D, we'll call that one point B. Okay, we could say if EC is perpendicular to AB, then EC bisects AB. All right, and there are proofs that we could work through on all these, but those would take quite some time to go through a proof on each of them. So reference that, save that for class or for your textbook there. The perpendicular chord bisector converse says if one chord is a perpendicular bisector, so just the converse of the above theorem, of another chord, then the first chord would have to be a diameter. So above we had, if it's a diameter, it's going to be a perpendicular bisector of the chord. Here we're saying, if it's a perpendicular bisector, then it's a diameter. Okay, so if we have something that's a perpendicular bisector, so let's call this W, X, Y, Z, okay, if WX is a perpendicular bisector of YZ, then WX must be a diameter. All right, let's go ahead and apply some of those, okay? First, using the congruent chords to find arc measure. So find measure of arc GH. Well, I'm using these 2 circles. So note that This first circle and the second circle, they're congruent because their radii are congruent. The chords are congruent, and therefore their arcs are also congruent. Okay, so this arc is 105. That means this arc, the arc GH, would have to equal 105 degrees. Okay, another one over here. So find ij and then find the measure of ij. So ij is a length of ij, so we're going from here to here. Well, notice we have a diameter intersecting at a right angle. That means it is a bisector of this. So therefore, if we called this point P, JP would be congruent to IP, meaning IJ would be 9 plus 9, or 18. Then MJ, or excuse me, the measure of IJ, so measure of arc IJ talks about the angle measure here. Well, remember, since we have a chord here that has been cut by a perpendicular bisector, we also will note that this arc is going to be congruent to this arc. All right? And one way to think about that is if you were to draw a chord here, this length would have to be the same as this length because 9 and 9 are the same. This is the same by reflexive property. So Pythagorean theorem shows that this arc or this chord is equal to that chord, meaning their arcs are also congruent. So 6x minus 17 is equal to 4x minus 3. Okay, and so subtract our 4x over, we get 2x minus 17 equals negative 3. Add 17, 2x equals 14. Divide by 2, so x is 7. And if x is 7, we're looking for the measure of the arc, so we have to find out what, let's go ahead and substitute in here. 6 times 7 minus 17 is, well, that's 42 minus 17, or 25 degrees. And right here we'd have 4 times 7, should be 25, right? Minus 3, well, that's 28 minus 3, or 25 degrees. So 25 and 25 is equal to 50 degrees. And that looks like 56 degrees. Let's try that. 50 degrees. There we go. All right. Okay. Using perpendicular bisector, let's find a point equidistance from each of the given. These are 3 points, and we want to know, let's say they're like shrubs or plants in your yard, and you want to figure out where to hit or put a sprinkler somewhere out here so that it actually hit each of these, right? A sprinkler kind of sprays in a circular fashion. You want to hit each of them without hitting maybe a pathway or your cars or something out here, okay? And so you don't want to overspray. Well, let's see, where can we put that sprinkler in order for it to hit all 3? All right. Well, if we were to draw in, and we're just going to sketch this, we're not going to construct it, but if we were to draw in these 2 arcs, thinking that they were, in fact, let's use a different color on that one, thinking that they are like chords. Whoa. Boy. All right, maybe I should have stuck with the first one. Thinking they're chords of a circle. So, you know, if we had this circle, now every time I do this, it's really, really bad, but you know, we have this circular shape cruising around here. Okay, and so now we have a circle. Right, if we were to complete it, we have this circle. Okay, and somewhere out here is the center of the circle. That's really what we want. All right. Well, if these were chords, then the perpendicular bisector of each chord would be a portion of our diameter, right? And so if you think of it that way, if I were to bisect this chord, if I could actually construct the bisector, mind you, but I'm just going to estimate it. The halfway is about there. Okay, and if I were to bisect this chord, about halfway is there. And then the line perpendicular would be the line that intersects that chord at a right angle. So I already guesstimated it's about right there. Now that's obviously not the best construction, method, you should use a compass and figure that out, or a protractor of some sort. I would use a compass, but I'm not going to do that on here. We're just going to kind of go with what we could do to figure it out. And so there's my perpendicular line. Extend that perpendicular line. It looks like right about there is our point of intersection, right? That is congruent to that. And so I would say the place to put my sprinkler would be right there. All right. And it would hit that, and that. Note that each one of these distances are the same. That's a radius. That's a radius. And that is a radius as well. So equidistance away. You get a little spray on the outer edge here. All right. Well, let's try one more here. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. All right. So if I have a chord here, once again, we'll call it AB. We don't want to break pattern, you know. And then another chord. Oh, excuse me there. Another chord over here. And we'll call that one unbelievable. Okay. Got a bit of a wavy line on that one. We'll call that one XY. All right. And then let's call the circle P. Okay. Well, if I wanted to find out how far away from the center XY was, I could draw, or I can construct a line from XY to point P and intersect it at a right angle. And I could do the same thing. Now these, in fact, I'm going to switch up where AB is just so it doesn't look like a complete straight line there. Let's there we go. Let's do something like that. AB. Okay. And I'm going to go ahead and hit that at a right angle. All right. And so if this distance right here is congruent to this distance, so let's call this M and N. So if PM is congruent or is equal to PN, then AB is equal to XY. So if this distance is the same as this distance, then these two chords are congruent. They're equal. Okay? That's what we've got right there. And the way we would figure out their distance is from the center to the chord at a right angle. And one thing to think about also, and this is probably something that will come up in one of your assignment problems, is that makes this chunk PM a portion of a diameter, right? Because it intersects the chord at a right angle. And PN is a portion of the diameter as well because it intersects at a right angle. Two differently drawn diameters, but definitely is part of them. So let's apply that. If I want to actually apply that, I say, well, in this diagram, we've got a circle. We know that TU is congruent to, or is equal to VW, which is equal to 8. So this entire length equals 8. This entire length equals 8. And since we have a perpendicular line, right, that's a portion of a diameter, which means it bisects it. So if this TU is equal to 8, that means TA is 4 and AU is 4. And if VW is 8, then we didn't put a point here. Let's call this, what do we do? We don't have C, what's you see? VC is 4 and CW is 4. All right. Well, if I want to find the radius of circle S, one thing I could do is I can think triangles here. All right. I can go, well, if I want the radius, this whole thing's a radius, or I could think, hey, If I draw in that line right there to the center, that line is a radius. And I have a right triangle right here. I've got 4, and if I knew this length, I could then find this length. Okay, or we'll call that R. Right? Well, I could find out this side length because I know that 7x is congruent to 4x plus 9. They're equal. 7x equals 4x plus 9. And I know that because my chords are equal. So if the chords are equal, they are equidistant from the center. That means subtract 4x, so I get 3x equals 9, and 1x equals 3. And if x is 3, then 4x, so 4 times 3 plus 9 is 12 plus 9, which is 21. Right? So this length right here now, that's 21. Okay? So if I redraw that triangle right there, we have R, 4, and 21. Now obviously this is not drawn to scale because these measurements don't match to what our scale is, but that's the measurements we have. So R squared is equal to 4 squared plus 21 squared. Okay? And 21 squared is 441. 4 squared is 16. So that means R squared is going to be equal to 457, which means R is equal to the root of 457. And if you round that, it would be R is approximately 21.4. It just depends what they ask, and if they don't ask, you're usually pretty safe at leaving in simplest radical form, but you could also write it as a decimal there. All right. Well, let's see. Yep, that's all I got for you. Good lucky.